I'm very happy to talk about the project simulation-based prior knowledge elicitation for parametric Bayesian models. And where we focus in general
one has to press it 3 times before it decides to work.
Okay. Thank you. Yeah, so the focus of my work is on math development, in particular to help so domain experts such as applied researchers to translate their knowledge into prior distributions for parameters in a Bayesian model. And well, do we actually need such a method? Well, when we think about simply a factorial design, then we might think that very likely the expert has some knowledge, for example, about the group averages or the treatment effect or the interaction effect. But the crucial question is now how we can translate this knowledge into the parameter space and then to construct prior distributions for the parameters. And this becomes even more difficult when the parameters are on a different scale, like on the log scale. And of course, this is not a new question or a new problem. It's actually a rather old one. And there exists a whole research strand working on exactly this question and working on methods to translate expert knowledge into prior distributions. Historically, most methods focused on querying the expert with respect to quantities of the parameter itself. And then the question is, how can we construct a distribution for the parameters based on this knowledge? Recently, there has been a shift to focus on the prior predictive distribution, such that we can ask the expert with respect to the outcome variable and the scale with which the expert is familiar with, actually, and then to translate this knowledge into the parameter space and construct prior distributions on the parameters in the Bayesian model. We try to combine both views by allowing the expert to give information on both the parameter space or the observable space. So actually the outcome variable or the scale of the outcome variable and derived quantities from this. Our work mainly builds on the work from the Silva and colleagues, Hartmann colleagues, and Manderson and Dowdy, I'm very embarrassed, I'm not sure how to pronounce it, who is actually also here today and will then in the next talk introduce the method, which I'm looking very much forward to. So, but at the moment, we are talking now about our method and how does it work? Well, in this graphic, we have a general overview of the mechanism. It's not important at the moment to understand this graphic in detail. We will go through each step. The high-level idea, nevertheless, is we have on the one hand an expert who we query with certain information. We get data, information from our expert. And on the other hand, we have a generative model with which we simply simulate exactly the matching information. And the goal is now to find a specification of our data generating model such as the discrepancy between our simulated data and the expert data is minimized. All right, then let's go through it step by step. We start with our generative model. We assume a very simple example. Namely, we have only one categorical predictor with 3 levels, say group A, B, and C. As such, we have now 4 parameters in our model, 3 regression coefficients, and then the standard deviation of our normal likelihood. And we assume a normal priors for our regression coefficients and an exponential for sigma. And now we want to simulate data, so we need certain hyperparameter values. Of course, we don't know them yet, because otherwise you wouldn't need such a method. So we start by simply having a random initialization of our hyperparameter values, such that we can simulate now in a forward way predictions from our model. In the next step, we can define the target quantities, so actually the quantities that we would like to elicit from our expert. And this can be on the parameter space, so with just questions about particular parameter characteristics, but this can also be on the observable space with respect to the outcome value or any other quantities derived from this. In this particular example, we assume we ask the expert with respect to R square. And on the other hand, we ask also with respect to the expected average of the groups. However, in general, we don't have direct access to this information from our expert, but rather indirectly by using a particular elicitation technique. And therefore, we have now the second step that we have to compute the elicited statistics, which results simply by applying a particular elicitation technique to our target quantity. So that means we can ask the expert to provide indeed the full distribution. This is histogram-based elicitation. However, we can also ask to provide us some quantiles or to provide us with moments like mean or standard deviation. For this particular example, we now assume that we ask the expert with respect to the histogram R square for R square and quantiles for the expected average of the groups. All right, so these are exactly this information that we would query from our expert. That is, now we can actually go ahead and compare these quantities with the data from the expert. Well, before we go now into the applied area, we have to validate our method and check whether it works as expected. Therefore, we started by simulating an expert. This is actually now a very simple idea. We simply assume that we have a ground truth. That means a specific vector of hyperparameter values, which we put into our generative model, and before the training simply once generate simulations such that we end up with a distribution for a square and our quantiles. And this data we put aside, and this is the expert data now. And now when we have this random initialization and simulation of our data, then we can compute the discrepancy between the simulated data and the expert data. At the beginning, this discrepancy will be, of course, quite high, but with the learning and the updating of the hyperparameter values, the discrepancy will decrease. And here we compute this discrepancy for each elicited statistic and combine it in terms of a weighted sum to get the total loss. And having this total loss, we can now compute the gradients with respect to our hyperparameter values and update our hyperparameter values accordingly. And here now we see the trajectory for the updating of our hyperparameter values. And we see also that after a certain number of epochs, we find a convergence. And we use the last learned hyperparameter values and then the average of it to get the final learned hyperparameter values. Yeah, and with this, we can actually now ask, well, what are the prior distributions that our method would recommend given this expert data? And as we are now in the convenient situation that we have this ideal experts or this knowing of the ground truth, we can really check it against what we actually gave as input to our method. And here we see now with the dotted lines or dashed lines the ground truth, and the solid lines are the learned prior distributions. Yeah, now we can of course ask, well, okay, this works for a toy example, nice, but what about more complex models? And well, we tried for a factorial 2 times 3 factorial design where we learned 7 parameters. Again, normal likelihood, but of course, very interesting would be actually to have models where we change the scale, because these are the models which are also difficult for experts. And indeed, here we have now also tried out our method for binomial likelihood with logit link and Poisson likelihood with log link. And finally, we wanted to challenge the method also by using multi-level models, and indeed, as well, we were able actually to learn the random effects based on expert data in exactly the manner as already introduced. Yeah, so from this, we can now ask where we go from here or want to go. There are 2 areas which are of particular interest for us. So from the conceptual level, it is still required at the moment, as you have seen that we specify the prior distribution family. And this is still a relatively challenging part, and we would like to have a method where we even omit this necessity. And combined with this, it would also be nice to have a method which just does not learn only independent priors between the model parameters, but a joint prior for all model parameters. Furthermore, at the moment we are focusing on one expert, but of course it would be nice to have multiple experts in the analyzers. And then it is important, and we are working at the moment very hard on it to provide informative diagnostics that we can give guidelines to the user of the method how to work on this whole workflow. This is already connected to the next level, maybe the implementation level. Of course, we want to have a user-friendly Python package, which are working at the moment. And nevertheless, I'm quite aware that a large part of the community is working mainly in R and Stan, and therefore I really want to have an interface to R and Stan such that it can be smoothly connected to the workflow in which people already have in the Bayesian analysis. And then it would be nice, of course, to have very useful default settings. And the method is very flexible. And this is a nice thing, but it can be a burden. In the moment when, for example, the method is very new, you don't know how really to customize it. And then it's important to have useful default methods that you don't have an extensive tuning phase, which is often associated also with machine learning methods. And that's actually it. These are now, of course, the people who are working on this project, Stefan Ralev and my supervisor, Paul Birkner. And just as an information, so we are working at the moment also on a project website where we will update all the information about the project, and where we also have case studies where you actually can also see the implementation. And but it's very new, so it's quite under construction. There might also some information missing and so on. But I think in some weeks you can look again at it, and you will have more up-to-date information about the stand of the project and the moment. Thank you very much.